Welcome back to Physics 142. In the last video, we realized that you can induce a current or a potential difference, all right, both of those, current and a potential difference, I should say, by changing the magnetic flux that's going through a loop. So this is Faraday's law here. It says that when we change the magnetic flux, right, or that's changing the magnetic field or the area or the angle between the magnetic field and the area, right? So by changing the magnetic flux, we can induce an EMF or induce a potential difference and therefore induce a current. But in the last video, we realized that we put a little minus sign in this law. And so this video is about understanding this minus sign. And that minus sign is often talked about as this thing called Lenz's law. All right, and so let's start and write down what Lenz's law is and then see if we can actually understand it. And I'm going to warn you, this is one of the more conceptually difficult parts of the course, but I'll say that in good news, it doesn't really get any harder after this. So let's give this a shot here. All right, so what does Lenz's law say? Lenz's law says that the induced EMF and the induced current are in such a direction that they oppose the change that produced them. All right, so let's write that down. We say the induced EMF and current, right? The induced EMF and current are in such a direction, all right, such a direction as to oppose the change that produced them. All right, so wow, what does that mean? All right, how do we understand that? Well, I think we can best understand this through a couple of examples. All right, so to start, I want to do an example. Let's just take a square loop of wire here. All right, so here's a square loop of wire. And let's put some magnetic field in that wire, right? So we'll start and we'll put some magnetic field. Let's do into the page here, all right? So we'll run some magnetic field into the page. So if I was to take a side view, all right, so maybe a side view here, all right, side view. We'll have this side over here to my right be the sort of into the page side. All right, and so then that means that we have some magnetic field going through this way. All right, so I'm going to call that I for B initial. All right, that's the initial magnetic field. So in this configuration, the first thing to think about is, do we have any current flowing in the wire? And well, the answer is no. If you just have magnetic field, just constant magnetic field, no current is going to flow in the wire. So what needs to happen to make some current flow in the wire? Well, the thing that needs to happen to make current flow in the wire is we need to change the magnetic field. Right? We need to change that magnetic field. So let's imagine first that we make the magnetic field stronger. All right, so let's make the magnetic field stronger. So, whoops, magnetic field here, I'm doing that in red. So at some later time, right, we increase the strength of the magnetic field. So I'll draw that with a longer arrow, and we'll call this B final. All right, so now we've changed the magnetic field. We've made it stronger, right? So if I was interested in sort of delta B, right, delta B, what direction would delta B be? Well, delta B is the difference between those, right? So maybe I'll do that in a different color just to make it really clear here, right? So this is delta B, right? It's the difference between them, and delta B is clearly to the right here, right? Delta B is into the page in this direction, right? So if I was to draw in, delta B here, right? Delta B would be into the page as well if I'm making the magnetic field stronger, all right? So then if we think about, well, what would the sort of flux be, right? Well, the well, okay, sorry. Let me rephrase that. So now let's think about how that would apply to our induced potential and our induced current, right? So if delta B is into the page, all right, what Lenz's law says is this is a change that's producing a current, all right? This is a change that's producing a current, and so that change should then be opposed, all right? And so what we're going to imagine is that any current that occurs in this wire is going to then induce a magnetic field that opposes this change. And so what you get is that the induced, we'll write this one in green here, all right? The induced magnetic field, B induced, all right, is going to oppose delta B. It's going to be in the opposite direction of delta B. Well, how do I get a magnetic field that comes out of the page here, right? That's going to the left. Well, to get magnetic field that's out of the page, that's going to be counterclockwise current here, right? Be out of the page, right? Would require counterclockwise current to give me an induced magnetic field coming out of the page, right? Be induced. So what this says is that the current here, all right, if we increase the B field, will be out of the, will be counterclockwise, right? We'll get counterclockwise current, all right? And that's because the induced magnetic field needs to oppose the delta B, needs to oppose the change, all right? So just to make sure that, you know, that it's a little complicated, right? Can we try to make sense of it? So what if instead I decreased the magnetic field, all right? So what if we have the same situation, all right, same situation, but now, and I start with my initial, here's B initial, all right, but now I make B final smaller, all right, B final smaller. What's going to happen now, all right? Will the current be counterclockwise or clockwise? Okay, hopefully you've thought through and had an answer. Now I'll go through it, all right? So, well, now we look at what's the change in the magnetic field. Well, the change now would be this way, right? Delta B, right? It got smaller. So delta B, the change is the other way, right? Delta B is now the change. And so remember, the induced magnetic field, whatever is induced, the induced current needs to create a magnetic field that opposes that change. So now we're going to need be induced to oppose the change, all right? And so now the induced field will actually be going this way. And how do you get an into the page? Well, an into the page must be clockwise, all right? So we're going to get clockwise current, all right, if we decrease the magnetic field, all right? So it's the change, the direction of the change that matters. If we're increasing the magnetic field, right, if we're increasing the magnetic field into the page, then I need to induce a magnetic field out of the page. And how do you do that? Well, you do that with counterclockwise current, all right? If instead I'm decreasing the B field, all right, how do, then I need to oppose that change. I oppose that change. The change here is now sort of out of the page, right, to the left. How do I oppose a change that's to the left? Well, I make a field that's to the right. How do I make a field that's to the right? I do that with a clockwise current. All right, so there are sort of few steps you got to go through every time to think through this, all right? You need to think, is the flux through the loop, all right, increasing or decreasing, all right? If the flux is increasing, all right, then you need to do something to oppose that, all right? If it's decreasing, you need to do something to oppose that. All right, so this is, you know, a little tricky, all right? So take your time, think about it a little bit here, all right? Let's do another example and see if we can understand this even a little bit more, all right? So now, for my next example, I want to think about a sort of a loop of wire, all right? Here's a loop of wire, and let's imagine taking a bar magnet and bringing it up to the loop of wire, all right? So we're going to take that bar magnet and we'll bring it in, you know, some velocity v maybe, right? And this bar magnet, remember, it's got magnetic field and it's got these magnetic field lines that come out of it, right? So there we go. And as you bring the bar magnet closer, that's going to increase the magnetic field, right? So what we could say is, well, initially we had some magnetic field, B, going through the loop, right? And as we bring it closer and closer, well, the lines are getting closer and closer together, right? You're going to enclose more lines, right? That's increasing the magnetic flux, right? So we would say the magnetic field, or it's technically the magnetic flux that we're increasing here, right? But the magnetic flux is getting increased, right? B initial, B final. And so that means delta B is to the right here, right? Delta B is now to the right. And so that means that we're going to have to induce something that opposes that, right? And so the current, whatever current is induced here, will create a magnetic field that opposes this change, all right? So we'll get a B induced this way, all right? How do you get a B induced that way? Well, that's going to require a current that sort of goes around the loop like this, you know, depending on your perspective. From the magnet's perspective, right? If we were looking down on it, you know, how would I draw that? How would I draw that? Yeah, okay. I'm just going to draw it with the arrows here. That's probably the easiest, right? There we go. So induce a magnetic field this way, okay? And I'd like to actually point something out here, all right? If you're inducing a magnetic field this way, all right, that's sort of the equivalent, right? If you have a loop, all right, with magnetic field going this way, that's basically like taking a bar magnet the other way, right? That would basically be, you know, something, right? A magnet with magnetic field going like this, right? And then what you would get is you get a north and a north, right? And we know what happens when you take like poles and put them together, right? This is going to be a repulsive force, right? So it's going to push back on whatever happened, right? So you're trying to bring the magnet in this way, right? It's creating, the current is sort of pushing back. It's resisting the change that happened to it. So, you know, I've heard people talk about Lenz's law. You know, you could say it's a very human law, right? It resists change. The more you try to change things, the more it pushes back. All right, so that's what Lenz's law is all about. Is that you end up inducing these currents that are resisting the change. Now, I should do one more example before we wrap up here. All right, so far, all the changes I've been talking about are just changes to the amount of magnetic field, right? Sort of dB dt, right? We're changing the magnetic field with time. But clearly flux, right? Flux, flux is not just magnetic field, right? Flux is B dot dA, right? Which is B times dA times cosine of theta. So B is not the only thing that you can change, right? You also could potentially change the area, or you could change the angle. So let's do an example of that. All right. So let's just move this up just a little more. All right. And so the example that I want to do here is let's suppose that I have the ability to make a square wire smaller, all right? Maybe by a factor of 2 or so. How much current, or would there already be any current generated, all right? It's, I think, a pretty fair question. So let's imagine, so here I've got, you know, my square wire again, all right? There's my square wire, and, you know, I've got some magnetic field in this wire again, like before, all right? But now what I'm going to do is maybe, you know, imagine that this part here, all right, this part of the wire is movable, right? So maybe I take it and I move it, I slide it over, right? So I slide it over so it ends up here. So now what I've done is I've, you know, sort of the final, if I sketch this now, right, it looks sort of like this. So now the loop that I have is half as big. Right, so now the loop that I have is half as big. All right, and the question is, well, what's going to happen here? All right, so I've changed the area. I've kept the magnetic field constant. Right, the magnetic field is not changing, but now I'm just changing the area. I'm reducing it in half. What happens? All right. Well, let's think through this. And again, maybe if I think about a side view, all right, let's think about, well, we start with some initial amount of magnetic field coming through, right? Or maybe, you think of that as some amount of magnetic flux coming through, all right? And as I change the area, what's going to happen to that amount of magnetic flux? Is it going to get bigger, all right? Or is it going to get smaller, all right? Well, the change in the flux, right? Well, at the end of the day, we have smaller area, so we're going to end up with less flux, right? Less flux. Now, flux isn't a vector, right? But I'll just represent it with an arrow here, right? Basically, we have less B field coming through, right? Or, if you think about B final, the total B coming through, right? It's going to be smaller. So that means the change, right? The change in the amount of magnetic field coming through, right? So I could call that delta flux or delta B, right? If I just think of that as the amount of magnetic field coming through, right? The change is this way, right? The change would be sort of, right? If this is my into the page, right? And this is out of the page, right? The change would be out of the page, right? The change would be opposite to the direction of that magnetic field, right? That would be the direction of the change. And the thing about Lenz's law is Lenz's law opposes change, right? So the change is out of the page, but we got to oppose that change. And so any induced magnetic field then is going to be into the page, and I hardly left room, all right? But maybe can fit it in there, all right? B induced, all right, then is going to be into the page. All right, induced is going to be into the page. Well, a current into the page, how do I do a current into the page? Well, that's going to be a clockwise current, right? That will induce a clockwise current, all right, I induced in the wire, because that will create an induced magnetic field that's into the page. All right, there's be induced, right? And it's into the page, it's the same direction as the actual magnetic field, but the reason that it's into the page is because the change was less, right? We were decreasing the amount of magnetic field, all right? And you have to oppose the change. You don't oppose the field, you oppose the change. And so that is the really key thing here, right? So I'll just, go through those steps one more time here, right? What's going on, if I'm decreasing the area, all right, that means I'm decreasing the amount of magnetic field going through, all right? Decreasing, a decrease is, we need to oppose the decrease, right? How do you oppose a decrease? Well, that means I put more through, right? And to put more through, that means I would need a current that's clockwise here, right? Clockwise current. So maybe that's another way to think through it here, right? You're always trying to sort of fix or resist whatever change happened. That's the essence here of Lenz's law. In the next video, I'll do one more example where we think about generators, and I'll do it by changing theta, all right? You could also change theta, but hopefully this gives you a good sense for Lenz's law. It's conceptually difficult, so it takes a little bit to work through. So I encourage you to come up, think about different ways that you can do this, right? But the key is that you oppose the change, all right? And that is how you figure out the direction of the current, and that ends up being super, super useful, and we will think about that a little bit more in future videos.